Okay, welcome everybody to the KVM roadmap session, otherwise known as RHEV Hypervisor. I'm going to talk about RHEV Hypervisor 7, which is for RHEL 7. My name is Noel. I am the engineering manager for the virtualization team in platform engineering. I don't know how many people went to Denise Dumas's talk yesterday on the platform, the RHEL platform roadmap. So I work for Denise. I'm in her organization. So what we're going to talk about today is how we engineer KVM at Red Hat, and what my team does, what the Virt team does, what components we work on, and how we engineer the hypervisor for Red Hat products. Then I'm going to show you some slides that I got from the performance team on performance and scaling of KVM. And then we'll go into the main section, which is the roadmap section. I'm going to focus on the hypervisor for RHEL 7. So first of all, about my team. Now this is what I'm really passionate about, is all the developers that work in my group. There's about 50 developers. They work on upstream code in the overall KVM community. They work all over the world. We have engineers in the US, in Europe, in Brazil, Australia, India, China, basically everywhere. It's truly the open source community, the open source model that you've been hearing all week at Red Hat. We live it, and I actually really love it. And what I want to convince you at the beginning of this talk is that KVM from Red Hat is actually the best engineered version of KVM out there, because it's all open source, but what we do to it actually makes it the best one. So talking about what my team does, I'll start from the bottom up, because I'm kind of a kernel person, so I think from the bottom up. We work in pretty much all these components. Whoops. Starting with the kernel. The engineers on my team are upstream maintainers of KVM in the kernel, VFIO, which is Virtual Function I/O subsystem in the kernel, vhost. There's also a kernel component up in the guest here, Virt.io, and we're the upstream maintainer there as well. We work in other parts of the kernel, like memory management, scheduler, timer, all to benefit KVM. Because KVM is a module in the kernel, and we leverage all the subsystems of the Linux kernel. The biggest piece we work on is probably QEMU, which is the user space that runs a virtual machine. It creates a virtual platform for each of the guest operating systems. There are a lot of subsystems in QEMU as well. It's its own project upstream. Very great community. I'd say 3/4 of the developers in my group probably work on QEMU as well as kernel and other things. Again, we're not the overall maintainer of QEMU, but we maintain several of the subsystems within QEMU, like the block layer, memory management within QEMU, things like that. QEMU contains things like I said, the platform structure, devices, emulated devices, as well as pair-virtualized device backends. Okay, another big component here is libvirt. Okay, that's the library that interfaces with the management tools, like RHEV and OpenStack. We have a whole team of engineers that work on libvirt. And we're really happy that it was chosen for OpenStack. So because OpenStack uses libvirt, it's become a very important part of the hypervisor and is getting a lot more contribution from other companies most recently. I want to talk a little bit about what goes on inside the guest here. So we have a guest kernel where I mentioned that we have Virt.io. We also have KVM clock, which is a pair-virtualized clock. We have other pair-virtualized functions inside the guest kernel. We also have, what you see there is QEMU-GA is the guest agent. It's an agent that runs in user space as a daemon. And it typically communicates through a serial port to libvirt, okay, to do some management functions. So things like you want to shut down the VM gracefully, libvirt will tell the guest agent to shut down. It participates in CPU hot plug, in live snapshot support. It does the file system freeze and thaw, so you get a consistent snapshot. It's an important part. Now I'll move over to the Windows guest, the blue one. We do work with Windows, and we have a relationship with Microsoft. We're not partners. We write the drivers, Virt.io Win drivers. So it's got the same, it uses the same standards for Virt.io. So it can talk to the same backends in QEMU. So there's a group of engineers. I think there's 3 on my team in Israel that work on the Virt.io Win drivers and 1 in Australia. Again, it's a distributed team. So another thing that's unique, but I think common at Red Hat, is all the developers that work upstream also work downstream. So they also backport their patches into the Red Hat products. Not everybody works upstream. It's kind of their choice, but we'd like to give them the opportunity to work upstream. There's a lot of people that like to focus on downstream type work. OK, I wanted to explain the RHEV Hypervisor name here. This is a branding thing, because KVM is not a brand. But also, the RHEV Hypervisor is part of the Red Hat Enterprise Virtualization product, but it's also part of RHEL OpenStack platform, okay? And we really wanted the exact same code, the exact same builds to go into both products. Otherwise, we'd be maintaining more software. So at the time, we thought, well, maybe we'll call it something different. But it turns out the marketing people, and I agreed with them, that the RHEV brand is really strong. Okay, so they kept the RHEV brand. They called it the RHEV Hypervisor because that's what it is. It's a hypervisor. And the only confusing part is I put in the caveat on the bottom is that there was already something called RHEV-H. Okay, you see some smiles. People know that there's an ISO that comes with RHEV-M that you can deploy a host. It's like a stripped-down version of RHEL. And some people confuse, when I say RHEV Hypervisor, they confuse that with RHEV-H. Okay, so I'll always spell it out like that, RHEV Hypervisor. If I say RHEV-H, I mean the ISO. I wanted to mention that as the guys on the team are working in the upstream, either kernel, QEMU, libvirt, they're working with a lot of different companies. We have strong positions in the upstream communities, but we also work with our partners in the upstream, with our competitors, like other distributions of KVM. We work with people who work on Xen, because Xen uses QEMU and libvirt. Everybody works together in the OpenStream community. The one thing that we don't talk about in the upstream community is what we do inside Red Hat. So I wanted to explain sort of the process that we go through to create the RHEV Hypervisor. OK, so I'll start with the way the kernel development works. So kernel rebases on every major release of RHEL. OK, so RHEL 6 was 2.6 kernel. RHEL 7 is now 3.10 kernel. And after that, all patches are backported from upstream. OK? We did the same thing with QEMU in 2.6, but the rapid pace of development meant that it got really hard to backport patches into QEMU. So we were doing something different in RHEL 7, and the best way to illustrate it is through the example of RHEL 7.1, which is the first update to RHEL 7. So we have been rebasing QEMU, okay? So in this example, RHEL 7 was QEMU 1.5.3, was based off of QEMU 1.5.3. We rebased QEMU to 2.1.2 for RHEL 7.1. And we don't just take it as is and ship it, okay? That's a misconception. But we number, we use that base number in the package name. But what we do is we disable some devices and we disable some features. So why do we do that? The upstream community, I mean, we're a good percentage of the upstream community, but we don't control everything. And there's some devices in QEMU that we absolutely do not want to support, aren't used by Red Hat products, maybe aren't maintained upstream. Now, there's a lot of crazy things that go on in the upstream community. And these devices are fairly easy to disable. You just configure them out. We disable certain features. So again, people program features. They somehow get into the upstream QEMU. They go away. They don't maintain them. They maybe aren't very secure or whatever. We affectionately call these the crap features that we decide that we don't want to maintain them. If somebody discovers they're there, they're going to use them, and then we're stuck maintaining them. OK, after that, there may be some features that we wanted to support in RHEL 7.1 that we didn't quite finish in time for this rebase. So we're still working on them upstream. And we'll finish something important that we want to backport into RHEL 7.1. And I was trying to think of a good example of this one, and I'll have one later. There weren't any big features, but they're more like feature completers, like things that just got that feature complete. Because if you know, upstream is like every single version has an additional feature that'll eventually make that feature complete. So meanwhile, every time we finish a feature, our QE team is testing it. Okay, so they're discovering bugs. There's people upstream that are fixing bugs. And we're constantly backporting bug fixes. When our QE team finds a bug, they file a Bugzilla. We work on it. We look for the fix upstream. Maybe it's already there. If it's not, we'll program the fix upstream. And we can't backport it into a RHEL product until it's upstream first. Okay, that's something that our team really strongly believes in. And the resulting package that comes out is called QEMU KVM Rev, and with the base version number. And then as we do fixes after that, you'll see dash, and you'll have more numbers for the asynchronous errata fixes. And what I wanted to point out is that QEMU KVM Rev only ships with Rev and RHEL OSP, okay? And we get a lot of confusion when people see that base version number. They, for some reason, assume that those are all features from upstream of that base version are in there, all devices, and they think that any feature that came after that couldn't possibly be in there. But you see the way that we do development, that's not true. So now I'll expand this out to show you the timeline of RHEL 7. So like I said, RHEL 7, and here's where I have to explain something else too. We do development on the RHEL release cycle. Even though we ship our package, QEMU KVM Rev, we ship it with RHEL and OpenStack. We actually don't ship this version of KVM with RHEL. Now, I might slip along the way and talk about the version of RHEL, but it's really the version of RHEL we've built this version of QEMU KVM for. I know it's kind of confusing, but if you run OpenStack or you run Rev, you know that it supports different versions of RHEL on the host. Okay, so the versions I'll talk about will be the RHEL versions. So in RHEL 7, we shipped QEMU The base version was QEMU 1.5.3. We had a lot of opportunity to backport additional features. We rebased early, but we do the same process for every release. We were able to backport some features way up to QEMU 2.0. I want to explain this little thing in blue. We kept the advanced features enabled. And the reason I put that there is because the version of KVM that we ship with RHEL has those advanced features disabled. So there's some advanced features like storage live migration, live snapshot that really need a management tool that's meant for a data center to manage those. Okay? So starting with 7.1, we started rebasing QEMU, and we chose version 2.1.2, like the example. We did the same process, took some things out, added some things from the upstream into it. RHEL 7.2 is what we're working on right now. I can tell you we've already done our rebase. It's version 2.3.0. And we're at the point where we haven't hit the development freeze, so we're backporting some features from QEMU 2.4 into the version of QEMU for, see, here's where I get mixed up. I just say we're backporting it to RHEL 7.2. The feature that I know of right now that we backported is memory hot plug, okay? So the version of QEMU in RHEL 7.2, built for RHEL 7.2, will have full hot plug and unplug support, even though it wasn't in QEMU 2.3. And it'll go on. RHEL 7.3 will probably rebase again, but maybe not. I mean, we're going to make this decision on every release. So in the end, I want to give a little bit of a history. Like KVM is a very mature technology, and I want to give a lot of thanks to RHEV for telling us what features to develop. RHEV has hardened a lot of features in KVM so that when OpenStack came along, KVM was really ready for OpenStack. It had a lot of rich features that were hardened by RHEV, and it actually took a while for OpenStack to actually request new features from us, because they were just consuming the features that we already had in there for RHEV. Now we're starting to see a couple of new features added to OpenStack first, and then adopted by RHEV. And because of this, KVM was adopted as the #1 hypervisor for OpenStack. I mean, it really had a solid foundation when OpenStack started. So I really hope I've convinced you that there's several other distributions of KVM out there, but I really believe that Red Hat delivers the best engineered version of KVM. So next I want to talk a little bit about performance and scaling. I hope some of you went to Shaq's presentation yesterday with Larry Woodman and probably others from his team. We work very closely with the performance team. They test KVM all the time. And RHEV Hypervisor for sure is the fastest, scales the highest of any hypervisor, and we have the benchmarks to prove it. These are the SpecVirt 2013 server consolidation results. There have been 14 results submitted, and KVM, Red Hat's KVM, has 10 of those 14 results. There are 2 yellow results mixed in there. That's Huawei's Fusion Sphere, and they actually use KVM. So I like to say that all the results are KVM except for the 2, and the 2 in blue are not KVM. The bigger one there says Power VM, not to be confused with Power KVM. This is IBM's Power VM, like their LPARs. So they have a result in there. And then the one on the very bottom is VMware. I guess they don't really care about performance and scaling really anymore. Another thing I wanted to point out, that the highest bar on the right, you probably can't read it, but people who can see the details on that slide ask why that's RHEL 6. Because you would assume that RHEL 7 beats RHEL 6 all the time, which it does. So that is an 8-socket result. And it turns out that's the only 8-socket result, because this benchmark came out before RHEL 7 was out. So they did the big 8-socket result with RHEL 6. And actually, the next slide, I think, zooms in a little better on that. So you see that RHEL 7 actually has the best 2- and 4-socket results, and RHEL 6 has the only 8-socket result. But we're number 1 across the board with this benchmark. So now on to the roadmap. So the funny thing here is that I was looking at this slide and I'm thinking, I'm going to talk about what we support now, what we've been doing in the past year, and what we're doing in the future, what's going to be delivered in the future. But what we're delivering in the future is what I'm working on now, or my team is working on now. What has been introduced in the past year, to me, is like past history. So I feel like I'm living in the future, okay? And you're probably living even further in the past than I am, so I'm sure a lot of people are still running RHEL 6. So I'm thinking of RHEL 7, 7.1 as the past, RHEL 7.2 is the here and now, we're working on it now. And RHEL 7.3, there's features that we're already developing for RHEL 7.3 and beyond. So my perception of time is a little skewed from the rest of you, probably. So the first feature I want to talk about is live migration. This is a very important feature for KVM. RHEL 7 was first supported by RHEV 3.5 and OpenStack 6. And one of the features that we implemented for both of them was the ability to do live migration from RHEL 6 to RHEL 7. Now this really took some expert engineering from within Red Hat, because we were going from QEMU 0.12 up to QEMU 1.5. So I have to say, we have the best experts in live migration technology on the planet to have pulled this off for the RHEV team and for the OpenStack team. After you get up to RHEL 7 and RHEL 7.1 and RHEL 7.2, they're also making it so that you can do live migration within the RHEL 7 family. And this is taking a lot of complicated engineering work. And they're teaching others in open source how to do this in the upstream. So how did we do this RHEL 6 to RHEL 7? One of the key things here is called the machine type. So when you create a virtual machine on RHEL, like RHEL 6.4, you get a RHEL 6.4 machine type, and it's set forever, okay? And then when you migrate it to RHEL 6.5, you still get the RHEL 6.4 machine type. And RHEL 6.5 knows, exactly what that means. So now say you have the RHEL 6.4 machine type, you've migrated up to RHEL 6.5, you migrated up to RHEL 6.6. Now you want to migrate it to RHEL 7. Well, we had to teach RHEL 7 about all those RHEL 6 machine types. There were also massive improvements in live migration technology between RHEL 6 and RHEL 7. One of the biggest ones I put a picture of over here, which is the live migration thread, okay, the M here. So these little circles represent the threads of the QEMU process. So if you have vCPU 0, vCPU 1, you have the migration thread and an IO thread. So when a live migration is initiated, you get this migration thread, and then it is responsible for moving all the guest memory from the source host over to the destination host. In the past, in RHEL 6, we didn't have a migration thread. QEMU used the IO thread, which was very disruptive to the actual execution of the guest during live migration. It also made it really hard to predict when the migration could finish and how long the downtime would be. And it was absolutely impossible to backport this technology to RHEL 6-based host. So we've had a few complaints from customers, and we work very closely with our support engineers and our solution architects out in the field. We've had some complaints about live migrations in RHEL 6 not completing or not, being down the amount of time that we promised it would be down, things like that. And we convinced a couple customers to upgrade to RHEV 3.5 on top of RHEL 7.1 hosts. We did some proof of concepts to show them how much better the migration experience is. And we've got some really good stories from that. RHEL 7 is definitely a much better migration. I think we're going to do white papers and all kinds of material about this experience. This is just over the past month or two. Some other improvements we did in live migration, we can throttle the guest in case it's not converging. Sometimes the guest OS or the applications will be writing memory too fast, and it can't quite make it over in the downtime that we guarantee. So you can now throttle the guest and make it dirty memory slower so that it'll make it over. There's this delta compression technology, which will end up sending fewer dirty pages across the network. Let's see. Oh, I wanted to do a call out here talking about collaboration within Red Hat. Obviously we collaborated with the RHEV team, the OpenStack Nova team to know which combinations of machine types and hosts that they needed us to test for live migration, needed the QE team to test. So this was a huge effort by our QE team. They started early. They tested all the different combinations that were required by RHEV and OpenStack, and they automated all of this and did some really bizarre tests that our engineers would never have thought to do, like live migration from RHEL 6 to RHEL 7, stopped the virtual machine, started again, migrated to another place. Oh, in that case, there's a bug. It's like, how did you think to try that? But the QE team has a huge test matrix for live migration, and so much of it is automated, which, again, I think makes the case for us having the best engineered version of KVM. So live snapshot active merge. We did this project in conjunction with the RHEV team. So first of all, what is a live snapshot? In my terms, it captures the disk and memory state at a certain point of time, and it creates QCOW2 volume chains. Okay, QCOW2 is the image format. I think a lot of people who run OpenStack will recognize QCOW2 because their image files say they have the extension QCOW2. So the picture there shows the QCOW2 volume chains, A, B, C, D. So we've been working on this technology in the block layer called block jobs for a long time. Again, it's iterative development. We get, features come over time. So we've done block mirroring. That's the basic technology for storage live migration. We've done snapshot merge. You can do snapshot merge forward and backwards through these volume chains. You can do them only to internal volumes, though. And finally, the engineers combined the block mirroring with the merge technology, and they were able to merge into the active layer. And the active layer is the one that the guest OS is actively writing to. So that technology took a long time to get going. It was, it took a long time to complete, I want to say. I mean, we were doing all these things along the way. We got a lot of pressure to deliver this quickly from customers. field account managers, we had a lot of complaints from the RHEV customers. We heard a lot about the customer requirements, and so we took this seriously and started an agile project where we had developers from VDSM, libvirt, QEMU, even from the OpenStack team, meeting on a daily basis to make sure that there was no blockers, that it was their 100% priority to get this project done. So next I'll talk about our NFV roadmap. We're doing a lot for network functions virtualization because they've embraced OpenStack. So now here's where we're getting requirements from OpenStack to do some new things. So there's two major configurations, the way I see it from my KVM perspective. The first configuration uses NUMA pinning, NUMA topology awareness, SR-IOV device assignment, and then DPDK running in the guest. The second configuration uses DPDK with Open vSwitch. It's a lot more flexible configuration, and it uses a technology that is in QEMU called vhost user, and I have pictures of all this. We have future work that we're doing with OPNFV, and I have the link to the KVM hypervisor project there. And last but not least, real-time KVM. Okay, it's a huge project on my team, very, very important, and I'll go over that as well. And that actually applies to both of those configurations and all future configurations. So NUMA pinning, NUMA topology awareness, SR-IOV device assignment. This is planned to be fully supported with RHEL OSP 7. This one is kind of weird because all the technology in the RHEV Hypervisor is done in 7.1. I guess the piece that was missing in OSP 6 was the NOVA scheduler. The NOVA scheduler can discover where the PCI device is assigned or where it lives in the host, and then schedule the guest to run in that NUMA node. So the kind of technology, this one is interesting too because VFIO device assignment was a big feature in RHEL 7. So this has been around for a while. It's not new in 7.1. Device assignment has a long history in RHEL 6. The VFIO part of it is new technology, but we've had device assignment for a long time. Also, we have the most brilliant engineer that maintains VFIO upstream that works for Red Hat. Some people hear this called PCI pass-through. It's not what we call it internally, but I just want to let you know that if you hear it as PCI pass-through, that's what this is. Some changes, a lot of changes in the libvirt API to pass the host NUMA topology up to OpenStack. Let's see, some kernel work that our team did. So huge pages. Huge pages is another feature that has been in RHEL 6 for a long time. You can have 2 meg huge pages. You can assign them to virtual machines. What we did new here is the 1 gig huge page. So newer Intel processors handle 1 gig huge pages. And we had a kernel developer on the KVM team, on the Virt team, actually do this work in the upstream kernel, which was really exciting for him. And he also made, it used to be that you had to specify huge pages on the kernel command line, which was kind of awkward and static. And now you can allocate them at runtime. Some work we did in QEMU was to align the guest to NUMA nodes. So you can actually have virtual NUMA nodes in the guest. If you have a wide guest, like 8 or 16 virtual CPUs, it's a really good idea to have virtual NUMA nodes. And if they align to host NUMA nodes, then you get optimal performance, especially if you pin all the virtual CPUs to host cores. So this was actually more joint collaboration. In particular, I would say we did a lot of work with our NFV partners on this one. We actually started working on this during RHEL 7. We gave them RHEL 7 kernels with changes in it. After RHEL 7 shipped, we were giving them new versions of QEMU and libvirt to test out to make sure, absolute sure, that we were providing the features based on their requirements. And they were testing all this code out for us. So here's my picture of NUMA pinning and topology awareness. So this is supposed to represent a NUMA node called node 0. And you can see the cores are in red. That's a socket. So a socket is also a NUMA node. And the virtual CPUs are pinned. And actually, vCPU pinning is one of those technologies that RHEV could already do. Has been around for a while. Same, yeah, so we just leveraged this for OpenStack for NFV. Now I duplicated this so you can see that it scales. Now we have 2 NUMA nodes. You can imagine 4 NUMA nodes, 8 NUMA nodes, and the Nova scheduler will place the virtual machine on the NUMA node that you specify, or will place it on the same NUMA node as the PCI device that you have in your guest. So this is an illustration of the first configuration. This time I'm highlighting the device assignment, or the PCI pass-through. Yeah. So we have the Intel card at the bottom. This is an illustration of what we were doing, or the performance team was doing in our lab. We have the IOMMU, which VFIO technology uses. And this is what isolates the guest memory from the rest of the host. It makes it more secure and isolated. So we use the IOMMU through VFIO, and the virtual function or the physical function or the PCI device is assigned all the way to QEMU, and the guest OS can access it directly using native drivers. So this is technology that's been around for a while, but now people are seeing how useful it is for DPDK. So you have, because you can use any native driver, you can use the DPDK pull mode driver in the DPDK library through an interface called UIO PCI generic. So let's see, last week these tests were run. The performance team did some tests with different NFV configurations that we can do today. They actually, starting from right to left, is the hardware maximum is 255. Bare metal got 218. Docker could get 215, and KVM got 208. And this is like really excellent results for KVM. Everybody was really excited back at Red Hat when we got these results. And this is a version of the 7.2 kernel, even though it says 7.x. Somebody didn't want to admit that it was a 7.2 kernel. But this is the kind of work and collaboration within Red Hat that we're doing for NFV. Collaboration with, in this case, OpenStack team and performance team. So this is the second configuration. This one is more complex, but I hope you see how it kind of builds on the first configuration. This one also has VFIO. In the lower right, you can see the card, instead of being assigned all the way up to the guest, it's assigned to Open vSwitch. Again, it uses VFIO. So the DPDK library actually uses VFIO as well. It's not just a KVM hypervisor technology. So what this does is it makes the network card or the virtual function able to be shared amongst multiple virtual machines. And how we do this is through a technology called vHostUser, which is part of QEMU. It is already upstream. It was part of RHEL 7.1. But through our joint testing with Intel, we found that we really need this feature called multi-queue to make it most efficient. Now, this is stuff that's happening right now, like right in the labs now. Like the previous result was the device assignment. This configuration is literally we're just getting all the pieces together to work so that we know that we need this multi-queue functionality. The multi-queue, this is an example of a feature that's in QEMU 2.4, the multi-queue feature that we're backporting to RHEL 7.2 so that we're sure we have it for this configuration. And the Open vSwitch upstream community is still, and DPDK are still working on supporting this. And we hope to have this ready for RHEL 7.2. So our future project with the OP-NFV group is, and this is led by Intel, to make KVM the hypervisor of choice for NFV. And this picture was taken right off the website that I put the link to again. So following from starting with 1, 2, then 3, number 1 is minimal latency variation. This is another way of saying real-time KVM, which I'll talk about, which we're already working on. The second one is inter-VM communication. People who know upstream QEMU will know this as IV shared mem. IV shared mem is one of those features that's been in QEMU for a long time, but nobody's maintaining it, and something that we don't include in our version of QEMU. We consider it, I don't want to say crap feature, because we've looked at it, we've studied it, we've decided it might be okay. It was lacking some security features with SE Linux. So we're looking at how to fix these problems. But through OP-NFV, we might come up with a different technology. And the third one is fast live migration. We've already been doing a lot of work to make live migration faster. Intel is starting to jump in. Intel traditionally has done work only for their chips in the kernel. We've been doing the QEMU work. Now they're starting to do work with QEMU to make live migration faster. One of the differences between the first configuration and the second configuration is when you do PCI device assignment, the virtual machine can't migrate. And this is listed in this project as something that that Intel wants to fix. So we're looking forward to that one as well, because it's been a problem for a very long time that different groups upstream have debated. There have been solutions, but they've been very particular to certain network cards. People bring it up, every 6 months as another project upstream to solve this. So it'd be nice to finally get this one nailed. And also, without introducing huge network latencies. So now let's talk about real-time KVM. Like I said, this is a huge project in my team. Our goal is to get really low average and max latencies based on our NFV partners, what they've told us their requirements are. And so what the team does is try to knock down the latency spikes so they can get that maximum latency down. So for real-time KVM, we have this all working in the lab. This is looking really good for RHEL 7.2. What you'll have to do is run the RHEL real-time kernel in the host. And the real-time kernel now includes KVM. It's the same version of RHEL real-time. And you'll also have to run RHEL real-time in the guest. Okay? I want to talk about the TuneD profiles, which I put a picture of on the right there. So we're leveraging the latency performance profile, which then is inherited by the network latency profile. These two, I think, already existed. And now we're getting a real-time profile. And building upon that, we have a different TuneD profile for the kernel in the host and in the guest. Now this I mean, if you watch Shaq and his team and how they do performance analysis, this is basically taking their brains and putting it in TuneD profiles. It is so hugely valuable to have these profiles, and they're all contributed upstream. So, Red Hat has basically given this knowledge of how to tune real time to the open source community. I just think that's great. And that's about half the battle of KVM, of real-time KVM, is getting everything tuned properly. The other half are all the patches that have gone in. When people ask me how the real-time KVM project is going, they're asking me how many KVM patches have we put in. And we really haven't done that many in KVM. We've done a lot of patches in the kernel, not in KVM. We've done patches in libvirt, in the TuneD tool, bug fixes for a library for Tuna. So we're just working wherever the code takes us. So huge joint collaboration. There's a separate real-time kernel team within Red Hat. We've become really good friends with them. With the regular kernel team, again, we're working with the Nova team. Let's see, Open vSwitch, real-time. We're going to have to incorporate all of this into real-time. Obviously, the performance team, I talk about them a lot. We work with them a lot. Again, with our NFV partners, we're going to do some kind of early access to give them access to real-time KVM, because we have to really understand that this is going to work in their environment. So here's one of those latency scheduler jitter plots that are fun to look at. So I want to go through from top to bottom. So the red lines are just plain RHEL 7.2 kernel as it was last week when they ran this test. You can see there is 3 big latency spikes. I've seen plots with a lot more than 3. I kind of wish they got more because it would have been a funner picture to show you. But they only ran this test for an hour because I didn't want to disrupt their development work too much. So that's what RHEL 7.2 looks like, which is not good for latency. RHEL real-time 7.2 is the green. It's very, very low average latency. There's you can see a few spikes in there. And then when you turn on KVM, the average latency goes up, which makes sense because you have to go all the way up into the virtual machine, so the latency is higher. But we're still doing really good. And we have little clusters of spikes that aren't that high. You can see they're not even getting up to 15 microseconds. So we think we're doing really good. The numbers that we got from our partners were well under those by now. But we still need to know what those little spikes are. So here's another chart that I got from the performance team listing the averages and the maxes of latency. And the first graph, you see that RHEL 7.2 has such a high max that you can't really tell, you can't really compare the low ones. So they took out the max so you can see what the average latencies look like. And here's where you can see that KVM is doing pretty well, right around 6 microseconds for average latency. Another thing I wanted to mention about this is all this work that we've been doing to lower the average and max latency has helped the real-time team as well. So they delivered RHEL 7.1 real-time. RHEL 7.2 real-time is going to be even better because of all the work we've done with them. So I was also curious because I get these questions about, how many fixes or changes have you made to KVM to get real-time KVM working? I wanted some actual numbers. So I had the project manager for this project get me some statistics. And they're all, embedded in Bugzilla and email lists. He just had to gather them up. And so I split them between kernel patches and non-kernel patches. And it turns out there's only 4 patches for KVM so far. All the other patches have been in the scheduler and the timer, and they've even been the KVM engineers doing this work. Let's see, ISOL CPUs is another thing that we talk about a lot in real time, because it's the way to isolate a CPU. And there have been only 4 changes, 4 patches in the real-time kernel. Okay, we're contributing almost everything up to the main Linux kernel. Only 4 are real-time specific. The non-kernel patches are a fix in IRQ balance that wasn't honoring the isolated CPUs, bunch of work in TuneD profiles, a new way to tune things because of the demands of this project, and 6 patches for libvirt. For libvirt, you want to be able to pin the I/O threads and set the scheduling level for the vCPU, not only the vCPU threads, but also the I/O threads. So you see that Red Hat has contributed over half of these patches that we pulled in, but I think it's a good number. I thought it was really interesting that all those patches were contributed by non-Red Hatters. I didn't actually analyze who's been doing the other work. It could be, a lot of times the case is the guys find the reason for a latency spike, go look at the kernel, found that somebody's already fixed it, and then they just backport it. So I want to mention really quickly some virtual storage improvements that we've made. Improvements for single virtual machine scaling, a feature called I/O threads. This is otherwise known as Virt data plane. And the first version of Virt data plane will be for Virt block. The second version will be for Virt SCSI. And the picture shows that you can now create multiple I/O threads. You can create any number you want. Typically, to start out, you probably want 1 I/O thread either per disk or per host CPU. And what this allows you to do is run I/O to those disks concurrently. And to do that, we needed a different locking mechanism, because it used to be that everybody went through a big lock in QEMU, so now each I/O thread has its own lock. And also, libvirt added the support to pin I/O threads. This is going to make a big difference in storage performance. And the RHEV team is implementing, embracing this feature for RHEV 3.6. So the last big feature I'll talk about is RHEV for power. You may have heard Denise talk about RHEL little Endian running on power. Now we're going to have RHEL little Endian running as the hypervisor host. So now my team had to get involved to backport all the patches from IBM upstream into the RHEL kernel so that we could run KVM little Endian. And we're planning to support this in RHEL 7.2 as the host, in conjunction with the RHEV 3.5, which already supports IBM's Power KVM. And starting with 3.6, we're going to try to be feature parity with x86 and Power. So you can have the same features for Power as you have for x86 running KVM. And you'll see the different guests. We'll support RHEL 6.5 Big Endian, because Big Endian is the native Endianness of Power. Little Endian is the new thing. We started supporting RHEL little Endian starting with 7.1. So now 7.1 and later, guests can be Big Endian or little Endian. So this is just a wrap-up of the features that I've already talked about and what version we think. If it has a star, it means it's a future version, and I can't promise that the feature will be in that version. But I'm pretty confident about the ones that say RHEL 7.2, because we're at the phase of development where we're pretty much sure. The final slide I have is about our future plans. First one is memory hot plug. Again, I'm pretty confident of this one for RHEL 7.2 because the code is in QEMU upstream already and backported into RHEL 7.2 QEMU KVM Rev. What I'm not as sure about is the Rev support. I know they're working on it for Rev 3.6. I'm not sure if they'll get the unplug support in. The next one, Windows guests. We really didn't talk that much about Windows, but there's a new version of Windows, Windows 10, and Server 2016. So developers in our lab are working on getting Windows 10 working, have found some interesting hypervisor issues there. We're pretty confident we'll get that done for 7.2. Okay, now starting on with the more future things. So things we're working on for RHEL 7.3, the Virt SCSI data plane, otherwise known as I/O threads. So I/O threads for Virt I/O SCSI. PCI Express bus. What you can do with the PCI Express bus, it has something called AER, Advanced Error Reporting, so that you can now tell the QEMU, the guest running in QEMU, that there's been an error on the PCI Express bus, so that it doesn't take down the whole host. It just isolates it to that virtual machine. And we have a partner that's working on that upstream. So we're helping that partner, reviewing the code, and helping it move along. Another big one that's been going on for a while, we've had this tech preview in RHEL 7, 7.1, 7.2. We are pretty sure it's going to be finished in 7.3, is UEFI support for the guest. So it's an alternate firmware. We currently have CBIOS firmware. We'll have an option at first to use UEFI firmware. And we don't feel like this feature is actually complete until we get Secure Boot support. And Secure Boot was actually a really interesting project between KVM and the kernel, QEMU, and the OVMF project, because you have to make sure that that firmware memory is actually secure. So post-copy live migration, that's making great progress upstream. There's a huge kernel piece that took about a year to get into the kernel. I don't know if you know about kernel development, but it can be a pain. You have to redesign things multiple times. We have a developer on the team that has a project called User Fault FD, which he got accepted into the kernel just a month or so ago. It's been backported to RHEL 7.2, so that piece is ready. Meanwhile, our QEMU developer, who's an expert in live migration, has been doing the post-copy live migration part. I think this is going to be part of the answer to the OP NFV fast live migration as well. I don't have time to explain post-copy live migration, but I'd be happy to if you see me later. So more future stuff. ARM support, we think OpenStack will drive this, not sure. But we have a couple developers working in the upstream for ARM. There's the RHEL sub-projects, so RHEL for ARM project. They've been working with those guys to make sure that virtual machines work on our version of ARM. Let's see, nested KVM is a great topic. I think this will be tech preview forever. The technology is really useful, but very complex. And again, the test matrix to be able to support this would be absolutely crazy. It's very useful in testing. So inside Red Hat, we use nested KVM a lot in testing. It's good for development. It's good for, actually really good for hands-on demos and labs, because you don't have to bring as much hardware, and you can teach people all about OpenStack. So we're supporting these kinds of things. It's just that we can't tell people to use this in production. Okay, and last, sorry, I only have a minute left. The last one I wanted to mention is virtual GPU. So our wonderful VFIO device assignment engineer got GPU device assignment working for RHEL 7 and 7.1. It's been a hugely popular feature. But we really want to be able to share a single GPU and not have it only be assigned to a single VM. And so we're working on it with multiple different vendors. We're not sure how this is going to work out. So before we go, I want to talk about 3 talks that are coming up. The next talk, there's an OpenStack platform talk in room 312, OpenStack engineering roadmap. After that, back in this room. And tomorrow, containers and virtualization in room 302. And that's, I guess, all the time I have. Thanks a lot for coming. I hope you're interested in KVM.